Good morning, friends and seniors. So it is about 11:30. So after half an hour, it is Christmas. So Merry Christmas to you all and advance Happy New Year 2023. So today we are going to discuss about, not in details, about a special type of valve which is called frozen seal valve. What is this frozen seal valve? Why this frozen seal name, frozen seal valve, all these things we will know. So here this is a axis symmetric drawing of the this is a 2D axis symmetric drawing of the seal, this fin tube assembly. Okay, so the valve portion, the valve will be here. The valves will be in the bottom. This is the bonnet, and this side also. This side also it will be bonnet will be there. Say this is the bonnet. Okay. So this is the bonnet. So liquid will be flowing through. Liquid will be going like this. Okay. And here your valve disc will be there, which will control the flow. So that part is different, because we know for a valve, basically for a flow control duty valve, we used to characterize it by that is called inherent flow characteristics. So your x-axis is relative travel of the disc and or relative opening, and your y-axis will be flow coefficient. So based on that, your valve sizing is characterized, that we all know. So that part we are not going to discuss today. Today we are mainly concentrating on this fin tube assembly. So basically this green line indicates it's a central line, and here only this color, I will define another color. Let's take blue color. So this blue color is the stem. Blue color is the stem of the valve. And at the end of the stem, the disc is connected. So say why this valve is required? Because when we are handling some hazardous liquids, that time, say another thing, the valve leakage class is given by any valve, control valve leakage class is given by FCI 70.2 standard. There broadly the valve leakage is classified into two categories. One is called seat leakage, means once this valve is completely closed, some liquid may pass through this here. When the disc will be placed on the seat of the valve, so from there some leakage may take place. So that is called seat leakage. Another thing is called gland leakage. This stem is inserted through some packing or gland, something like that. So from there the leakage also will take place. Say in this case some liquid is coming out like this. So that is called a gland leakage. So all the leakage class is defined in this standard, FCI, Fluid Control Institute standard, FCI 70.2. So, but here you see this seat leakage is not that much important or not in our interest, because it will be inside the line, not that much problem. But if there is a gland leakage, then it will be very difficult. It is dangerous. because it's when the liquid sodium, it will come out and it will come to the contact of air, the oxide formation, which is a exothermic reaction, and activity also maybe there something in secondary side. So due to that reason, our gland leakage, we should design a valve where the gland leakage will be absolutely zero, and it should be fail-safe. In any condition, there should not be any leak. For that, this fin tube is designed, and in the center of the fin tube assembly, the stem is inserted. This blue portion, okay? And this red line, there is a very small annular gap. Deliberately, we are allowing the sodium to raise through the annular path, okay? Why we are doing so? Because due to line pressure, when the sodium will start to travel, sorry, my pen means, so when sodium started to travel like this, okay, and due to this fin assembly, because fin basically it's a kind of extended surface heat transfer, we are increasing the surface area. So the heat augmentation, the evacuation of the heat enthalpy from the annular path, say the sodium is filled here, so whatever the enthalpy, it will be evacuated out. If it can be augmented and the sufficient heat can be evacuated from the sodium which is rising through the annular path, and before reaching at the gland, if the sufficient heats are evacuated and the temperature of the sodium is coming down below some 96 or 98 degree Celsius, around 90 degree, then the sodium itself, it will get freezed, and by freezing this liquid itself, it will be giving your it will be leak tight, perfectly leak tight, okay? So this is the basic concept behind this design of the frozen seal valve. So other parts are this bonnet part, disc, all these things, and in the top of the stem there will be some actuator. Basically it's a gate valve, okay? So the challenge of these things is to design the fin, because why? Because here, you know, when the characteristics length of a geometry, if the geometry is standard like spherical or rectangular or something like this, where the characteristics length of the geometry is known, there we can apply the Nusselt. And here the heat transfer, basically there are three modes of heat transfer: conduction, that is based on the Fourier's law, and the convection based on Newton's law of cooling, and your radiation based on the Stephen-Boltzmann formula. So their emissivity also is a critical factor, but here in my analysis I have neglected the radiation, the heat evacuation through a radiation. The major heat transfer through the fin, it will be contributed by conduction and convection. So conduction is depend on the thermal conductivity of the fin material, which is more or less constant, okay, in the Fourier law. But in Newton's law of cooling, H, which is Convective heat transfer coefficient, basically that is the function of temperature and flow okay, QL, you can something. So if the temperature is high, your heat evacuation also high through convection. It is normal virtue of heat transfer. And if there is a flow, very quickly, when a hot food we are taking, food we are giving, means it is getting the heat transfer is augmented. That's why the convective heat transfer coefficient, broadly, it's a function of temperature and flow. And another thing, what I was telling, if the geometry is a standard, like a spherical, rectangular, or something like that, where the characteristics length is known, there we can apply the Nusselt number, the conventional regression formula of Nusselt number to estimate the convective heat transfer coefficient. But here you see the geometry is very complicated, very much complicated, where one fin is stacked over other. Then how to estimate that heat transfer coefficient? Challenge is there. So I'm not going to give you the exact dimension. I have developed one fin and it is validated. Because this from this so far whatever I discussed, you might have conceptualized to find out the overall convective heat transfer coefficient of the fin. And if we want to calculate it by analytical method, then it is very difficult, because one side is flow, another means mass flow, heat transfer, okay, and it is not uniform. So here one fin, so when the liquid is here, this fin will be contributing. Then when liquid is going up here, then another fin, it will come into picture, and this heat transfer coefficient, because here temperature, some heat will be evacuated by first fin, then in the second fin temperature will reduce, so here the convective heat transfer will further reduce. So like that, the convective heat transfer along the vertical line, it's not constant. So if you want to calculate these things by analytical method, you might have understood how difficult it is. So today CFD and finite element modeling, the softwares are available. So I have used few tools. I have used some COMSOL. I have used COMSOL, CFD module and heat transfer module. So they are Navier-Stokes equation, momentum equation. It is solved when the velocity field in the heat transfer is coming from that by solving the Navier-Stokes theorem. So based on that only, this convective heat transfer coefficient is estimated. Okay, so today we are basically going to discuss other part. The valve portion is very simple. It's a normal gate valve, but the challenge is to design the fin, because if you increase the fin, if you increase the number of fins, so it will be very, now you see from a forge you have to machine it, because here welding is not advisable. There will be thermal resistance will be added, and this will further contributing the loss. So you have to take a forge, and that is to be machined. It's very difficult and costly. So more number of fins, to add more number of fins, it is not economic, and to increase the fin length, it will reduce the efficiency of the fin. So the number of fins based on to make the desired height of the fin tube assembly, so that the sodium is get freezed as early as possible. So in one hand we have to optimize the number of fins as well as to optimize the the marginally the fin length also to be selected, otherwise it will be fin will be inefficient. So for that, this I have modeled it, and I have used one open source plugin called Energy 2D, and after that I have written my own code in Python and MATLAB to verify it. Okay, so we are going to discuss that things in the now we will understand the fin dynamics, the basics of fin dynamics, and how this temperature along the fin, it is depend on so many factors, as I told, and how it is before reaching here, whether the temperature is coming down the freezing point of the sodium or not. Okay, that we are going to discuss. So basically, as I was telling, it's a special type of gate valve used to control the high temperature sodium flow in the secondary sodium system in fast reactor, to isolate, basically to isolate the steam generator from sodium flow during its maintenance. If there is a maintenance of the steam generator is required, then it is to be isolated. So that time, basically the SG outlet, there only this frozen seal valve is installed. Okay, these valves are known as frozen seal gate valve, not butterfly. Here in our case it is gate valve. A circular disc is perfectly fitted in the valve seat provided in the sodium pipe. The disc is attached to a cylindrical stem to provide stroke. Okay, so this will be going up and down. The stem is covered by a sheath which itself attached to the sodium pipeline, as I explained already. Okay, so to avoid the sodium leak through the gland of the valve, the liquid is forced to freeze in the annular path while it's raising. To promote this phenomena, the heat transfer through the sheath is needed to be augmented. This is achieved by providing the circular fins attached to the outer surface of the sheath. As I told, the large number of fins are uneconomical. Fins of larger diameter, means this length, if it is more, then it will reduce the efficiency. So it is to be the number of fins and the length of the fin, it is to be optimized. Okay, so now we will, so this is a typical cross section of a fin. It is like this. So now we will understand the dynamics of the fin. Very simple way. So this is the thickness T, this is the thickness T, and this is the length of the fin, and say this is the width of the fin. We have considered it as rectangular fin. Then you can, if we can, because to understand the dynamics simply, I have considered this. Okay, now some consideration. So here Q is the heat transfer rate, the H is the convective heat transfer coefficient, delta T is the temperature difference, and the area of cross section. So area of cross section in this case, so this is the width and thickness, so W into T, and theta is the temperature excess, which is the instantaneous temperature. Here somewhere anywhere the instantaneous temperature minus ambient temperature, and the perimeter will be, you know, this 2 into W plus T, so that is denoted by P. Now the boundary conditions for the and the assumptions for the modeling. So now my X is, and here, you know, heat can transfer any direction, but for simplicity to understand the dynamics, I have considered the heat is only transferring through this direction, which is X direction. Okay. This is one assumption, and it's a fair assumption. Okay. And at the base here the temperature you can consider that is the liquid sodium temperature. That means at X is equal to 0. So here X is equal to 0, or you can consider here X is equal to 0, and here X is equal to L. This is the length of the fin. So at X is equal to 0, the theta is theta B. What is theta? Theta already I defined. Theta is instantaneous temperature along the x-axis minus the ambient. So at X is equal to 0, your temperature excess is equal to theta B at base. And T infinity, considering the ambient temperature is constant, and here also considered the H is constant, and T is A, and the temperature will be varying along the fin. So here you will get high temperature, here less, because the heat will be evacuating, convected out. Some heat it will be by conduction, heat will be moving X direction, and in the Y direction, all the direction, this will be convected out. Okay. So this is the consideration. So as per the Fourier's law, your Q is equal to minus K dt by dx. So at X is equal to L, is equal to this, how much it is conducted. So here, how much it is conducted. At X is equal to L, it will be convected out through this area, tip of the fin. So that's why it is your Q is equal to, at here this is also one boundary condition, Q is equal to, so that means what I mean to say like this. So this is cross section A. So whatever heat will be conducting here, so that is minus K dt by dx is equal to that to be convected out through this cross section. So H A delta T. Okay, or you can tell that is, now your theta is equal to instantaneous temperature minus T infinity ambient temperature. This is constant, so your d theta by dx is equal to dt by dx. So we can write HA theta at X is equal to L. Okay, A cancel. So this is another boundary condition. So that's why it was written. So here the two boundary condition we will apply. One is at X is equal to 0, your theta is equal to theta B, which is nothing but the liquid temperature at that point, and at x is equal to L, your Q is equal to H theta at x is equal to L. Theta at x is equal to L. Now if we take one small cross section, one very small cross section, so this is the cross section, one slice if you take, say that is del x, okay, so it is along the periphery, this side, top, bottom, both the sides. So say here the heat is entering. So if you see the energy balance equation, so this is my energy balance basically. So say here the heat is entering is Qx, and after that here, so it is Qx plus del x, because this is del x. So now if you equate, so your Qx, so your Qx is equal to Qx plus del x plus Q convection. So convection is happening through the periphery, here, 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 that side and bottom side, okay. Now if we expand this by Taylor series, then you will get this Qx plus del x is equal to Qx plus dqx by dx into del x plus Q convective. So this Qx cancel, so you get a first order differential equation, dqx by dx into del x plus Q convection is equal to 0. Okay, then we know Q is equal to HA delta T, and here area, the surface area, our consideration, we have taken a small slice del x, so perimeter into del x. So we are substituting that value here, we are substituting, and here we are getting, you know, this Qx basically it is again it's again the function of Q is equal to, as per the Fourier's law, it is minus Ka dt by dx. So by putting all these things, if you simplify, then the things it will turn as, whereas this T minus T infinity is theta, so it will come d a ulta likh diya. So it is, here it is wrong, so it is d square theta by dx square minus h p by k into theta is equal to 0. Okay, so this called the fin parameter, this hp by ka, which is m square, is called the fin parameter, and this is a simple differential equation, d2 theta by dx square minus m square theta is equal to 0. It's a simple differential equation whose solution is theta is equal to some constant into cos h mx and b sin h mx, and the first boundary condition was at x is equal to 0, your theta is equal to theta b. So if you put here x is equal to 0, a turns to theta b, and for the second boundary condition, the second boundary condition was q is equal to h into theta at x is equal to L. So we need to find out this d theta by dx. So that's why it is this equation after putting, so here theta is equal to theta b cos mx plus b sin h mx. So if you differentiate that, you will get you will get this d theta by dx, and here you put the value, and as I told, at x is equal to L, the convective heat transfer is nothing but the convective heat transfer coefficient at the tip of the fin. So if you do that, then your B, it will come equate as this. But here we are considering that the heat transfer at the tip, here it is neglected. Normally for any type of fin, it is considered as the tip of the fin is insulated. It is called fin with insulated tip. Okay. So our H tip is neglected, can be equate to 0, and your B is become like this. And now if you substitute the value of the constant A and B, the instantaneous value of theta is equal to theta V into cos H mx minus ml by cos H ml. Okay, so this is the solution. Now Q of the fin, how much it will be evacuating, so that can be find out, that Q at x is equal to 0, because that much only, that much heat only it will evacuate out. So by solving this, your Q fin is like this. And the maximum, how much? The maximum is if the entire everywhere your temperature, whatever the base temperature, if it is not reducing. Why reducing? Because there is some losses. Correct. Because that convective heat transfer, it is varying. So maximum, how much? If it is the entire fin temperature, if it is theta V, that much only maximum heat will be evacuated out. Correct. So this is the maximum. So now the efficiency, of the fin, is Q fin by Q maximum, which is like this. Okay. So this is the fin efficiency standard. And Q no fin, if there is no fin, then the entire, only that tip through tip only heat will be evacuated. So it is like this, HA delta T, and the effectiveness is this much. Okay. So here it is very here it is very easily it can be understood that if the length of the fin is L, if it is increasing, so it is in denominator, so the efficiency will reduce. Okay. So that is the thing. Now I am not explaining that what are the boundary conditions is given in my simulation study. So here, as I told, our model study, we have used Energy 2D on open source code. It's a National Science Foundation funded open source software has been used to find out the surface temperature distribution through the fin radially. Okay, and these are the some parameters. So here it is buoyancy approximation is used in each fluid cell. Okay, means when it is meshing, each cell buoyancy approximation is applied, because it's a natural convection, gravity, it's a natural convection. So you see, this is one snap of that Energy 2D. So here these are the fins, and here the temperature is taken. Okay, and this is the model study of COMSOL. You can see at the base the temperature. So now if you plot, this is the x-axis. So say this is the x-axis. This is the x-axis. If you plot here temperature will be very high, and while it is going away, it is come down. Similarly, if you plot here the temperature in the annular path, if you plot, so this is my axis, and here the height is 0. Just sodium start to enter, so their temperature will be high, and after these things here it will come down. So this temperature I need, it should be, so this temperature, if it is T, this temperature should be less than 98 degree. So my number of fin and all these things calculation should be like that. So this is a COMSOL study, as I told, a COMSOL model. So here you see the base temperature is around 473 degree, and it is coming 435 degree, something like that. Okay, and as I told, this is the multiphysics simulation to estimate the heat transfer coefficient and this is a steady state analysis. You know, it is for transient, it will take, because it's a very huge, if you do mesh, it's a huge volume. The degree of freedom, it will be very, very high. So normally in normal PC, it can't be, the solution will not converge normally for transient study. You need cluster or supercomputer. So that in my lab I don't have. I have to book it. I have to book the slot. So simply I have done the steady state analysis. So this curve is showing the liquid temperature versus the heat transfer coefficient. You know, as I told, it's a function of temperature. So at low temperature your heat evacuation is less, and once your temperature is high, it is also high. So these are the some calculations we have used. This is the coding in MATLAB to find out all these things. Okay, and another thing is the gap, the annular gap. So it is quite obvious. If your annular gap is high, so very quickly your sodium will flow, will raise. By that time it very quickly it will reach here. So that much temperature may not be augment. So this is the gap. You see, if your annular gap is 0.25, okay, that is the bottommost curve. You see the temperature is here something around 60 degree, and here it is something around above 100 degree. So how much gap is to be given? That is also to be studied. So from the study we have estimated that the annular gap is 0.25 mm. So if you give that for that particular geometry, it will successfully, it will work. And based on all this study, I have designed the fin and it is tested also, and it is giving perfectly. Physically we tested, and it is giving the desired thing. So this is all about the frozen seal valve, to design the fin tube assembly, and how to design, and what are the criteria, where the frozen seal valve is used, all these things. So hope it will be useful to you all. Thank you so much. Good night.